Prezados, bom dia. Então, neste momento, seguimos para a primeira palestra internacional desta manhã, sobre modelamento de crescimento de grão pelo método de Monte Carlo, a ser ministrada pela professora Dana Zöllner, na forma de uma transmissão de vídeo. A introdução da segunda palestrante, a professora Dana, será realizada pelo professor Paulo Rangel Rios, na forma de um vídeo também.
Todos aqui me conhecem, eu sou o professor Paulo Rangel Rios e eu vou fazer uma pequena apresentação sobre a professora Dana Zöllner. A doutora Dana Zöllner vai falar sobre Modeling Grain Growth of Monte Carlo Method, quer dizer, modelamento do crescimento de grão pelo método de Monte Carlo, no congresso que está sendo organizado aqui pela UF, Escola de Engenharia Industrial Metalúrgica de Volta Redonda. Eu não resisti a botar uma foto que foi tirada em 2014, em Magdeburgo, comigo aqui, a doutora Dana Zöllner e o doutor Peter Streitenberger, um grande amigo meu. Então, atrás está o Museu Otto-von-Guericke, em Magdeburgo. Otto-von-Guericke, ele foi aquele sujeito que descobriu o vácuo, né? Aqui está a famosa experiência dos hemisférios de Magdeburgo. A doutora Dana Zöllner recebeu o doutorado dela em 2006, dessa Universidade Otto-von-Guericke, OVGU, em Magdeburgo, Alemanha, quer dizer, a Universidade de Magdeburgo. Ela obteve a habilitação dela em 2015. Para quem não sabe, a habilitação, depois que você faz o doutorado na Alemanha, você ainda tem que trabalhar uns anos e fazer um exame chamado exame de habilitação, e só com esse exame que você pode orientar teses, senão você não pode orientar. Ela, e outras também, ganhou uma professorship na própria Universidade Otto-von-Guericke. Em 2016, ela foi como pesquisadora para a Universidade de Dresden, uma cidade, aliás, muito bonita, que eu estou mostrando aqui uma foto do centro de Dresden. Esse centro foi totalmente destruído, essa catedral, não tinha nada dessa catedral, acho que só sobrou a base, por causa do bombardeio, e foi totalmente reconstruído, uma cidade muito bonita. Em setembro de 2020, ela retornou a Magdeburgo como coordenadora científica. Então, o grande foco da pesquisa dela é a evolução microestrutural de materiais policristalinos durante a deformação, recristalização ou crescimento de grão. Ela junta várias coisas, né? Experimentos, teorias analíticas e simulação computacional, e trabalha numa grande variedade de materiais nanocristalinos, biomineralizados, como conchas, por exemplo. Aqui a gente mostra a superfície de fratura de 3 conchas diferentes, como curiosidade, no trabalho recente que ela publicou. E, finalmente, ela publicou mais de 50 trabalhos científicos em boas revistas internacionais, incluindo artigos de revisão, e apresentou mais de 100 aulas, né, como essa que ela vai proferir agora, contribuições para conferências e institutos de pesquisa. Ela se deu o trabalho de gravar uma aula que acredito que vai ser muito útil e está muito bem explicado, tanto para aqueles que são da área de modelamento, como aqueles que têm um interesse geral no assunto. Aproveitem. Obrigado.
Welcome to my lecture about modeling grain growth by using the Monte Carlo POTS model method. In this talk, I will give you a short introduction into the POTS model, starting from a more general perspective, why we would want to model grain growth anyway, and then coming to the history of the POTS model before taking over the main part, where I will talk about how the Monte Carlo POTS model algorithm works and what the problems and possible solutions are. And finally, I will add some comments on possible applications. First things first. Most materials properties, like yield or tensile strength, but even toughness, hardness, etc., depend on the grain size of a polycrystalline material. Hence, understanding and controlling such materials' microstructures and therewith the grain size are a key to improve materials' properties. Now, the problem is shown here in this image. You can see how the microstructure changes over time. And this is precisely a problem. It's called thermally activated grain boundary migration, or grain growth simply. And this is a very complex problem, because if you look more closely, you will realize that all grains in a polycrystalline material try to shrink. From a thermodynamic viewpoint, it simply reduces their surface energy. Hence, the smaller a grain is, the stronger it pushes its atoms to its neighboring grains. And as a result, yes, we have a very complex 3D problem, because we do have a network of grain boundaries. From a global perspective, we have volume conservation. So the total volume of all grains stays constant. And when we look more closely on a local viewpoint, we have an equilibrium at the grain boundaries, which means, for example, if all your grain boundaries in a 3D polycrystal have the same grain boundary energy, then you'll have the triple lines along which 3 neighboring grains meet. And when you look at the grain boundaries along these triple lines, you will see that there are dihedral angles of 120 degrees. And while the microstructure changes over time, the global network has to keep volume conservation as well as this equilibrium at the boundaries. So if we know this, why would we want to use computer simulations in particular? Well, we know that the experiments simply show us what is happening. On the other hand, analytic theories usually show what we think is happening, and more often than not, there is a clear gap between the experiments and basic analytic theories. So we want to use in particular mesoscopic computer simulations that work on the grain level in order to widen our knowledge and close the gap between experiments and theories. Those computer simulations give us not only an insight into the fundamental physical processes of grain growth, but also of recrystallization or Oswald ripening. In addition, they give us information on morphology of individual grains or topology of whole grain microstructures, which can usually not be obtained analytically. And last but not least, or for me, one of the most important points, is that such computer simulations allow a far more precise manipulation of materials parameters than can be realized experimentally. So you see, there is really a need for solid computer simulations that enable us to recreate grain growth, but also recrystallization or Oswald ripening. And to that aim, I have picked the Monte Carlo POTS model. And you'll see in the upcoming steps where this simulation method comes from and how it works. I'm a huge fan of the Monte Carlo method. Of course, there are more that you could choose from, but I will show you that the Monte Carlo POTS model is in its basics quite simple, but can be applied to many problems, to really complex problems. How did it evolve? Well, the first application in physics of the Monte Carlo method was in solid-state physics for ferromagnetic materials, where the magnetization is represented by spins in two different states. You just have a state up and a state down. This model is called Ising model, and it originates in the year 1925. More than 25 years later, Potts generalized this Ising model and allowed not just the two states up and down, but Q states per spin, basically representing the local crystallographic orientation of a grain. Hence, this model is basically a Q states Ising model. But to honor Potts and his contributions and to also make the stochastic influences clear, usually everybody talks about the Monte Carlo Potts model for grain growth. But also if you hear just somebody talking about using the Monte Carlo method for grain growth, it's exactly the same method. How does it work? For the basic algorithm, we need only two materials parameters. The grain boundary energy, gamma, per unit length in 2D or per unit area in 3D, and the grain boundary mobility, m. Both depend on the misorientation angle between two neighboring grains. So exactly what Potts put in it was to use not these up and down spins, but this crystallographic misorientation that you can see here in this simplified scheme. Now, in addition, you can see that I put down here two equations, one for the grain boundary energy per unit length and one for the grain boundary mobility. Of course, if you want to go into more detail, you can take, for example, exactly your parameters from an experiment. But basically, you just need this precise information. After we have information about mobility and energy of the boundaries, we need to put down some basics for our simulation. What kind of lattice do we want to use? Because the Potts model is a lattice-based model. So what's easy to use is in 3D a cubic lattice or in 2D a simple quadratic lattice. Secondly, we have to put down the number of lattice points that we want to use. Yes, I have given here a number of lattice points n in 3D larger than 250 in each direction and in 2D more than 2000 in each of the two directions. Of course, you can take more. The number of lattice points is important because you want to model your grain microstructure as well as possible. So it's basically about the resolution of your grains. Each grain should be represented by a large enough number of lattice points. But it shouldn't be too large because your lattice points do not resemble atoms. This is precisely where we come to the point of what is the smallest size unit. And the smallest size unit is called a Monte Carlo unit, abbreviated as MCU, and it resembles one lattice point, which is a cluster of atoms of a grain, not individual atoms. So the resolution should be good enough for you to say something about the morphology of the grain, the morphology even of your grain boundaries, but you shouldn't go down to the atomic level, which is also not possible, as we'll see in a moment. Each of these lattice points has a certain number of nearest neighbors, and I prefer to take in 3D 26 nearest neighbors. So you can imagine it as a cubic lattice and you go for your first nearest neighbors left, right, up, down, to the front and to the back. And then you have the second nearest neighbors, which are slightly further away in your lattice, and then the third nearest neighbors. And in 2D, I usually take the 8 nearest neighbors, which are the first and second nearest neighbors. Now I've said that we shouldn't go up with our resolution too much because the smallest time unit of the simulation is called Monte Carlo step. MCS. And it is basically n reorientation attempts. And this n is precisely the total number of lattice points that we've seen up here in this slide. Which means the better your resolution, the better the resolution for each grain, the more reorientation attempts you'll need to make to have one simulation time step. And this means that the better the resolution, the longer your simulation will take. So the question arises, what are these n reorientation attempts? Basically, each reorientation attempt itself consists of 4 different steps. In the first step, we select a lattice point completely at random. And we choose, of course, from all lattice points in our lattice. This lattice point has a certain orientation, let's say Q mu. Now, we want to model grain boundary migration, where atoms or whole clusters of atoms change their orientation from a certain grain to a neighboring grain. Hence, if we look here on the left at this image, we see that there is this yellow grain, and we've picked precisely a lattice point completely within a grain. Now, of course, if grain boundary migration means that we are going to change the orientation to a neighboring grain, in this case, there is no neighboring grain. Hence, if the lattice point is on a boundary, we proceed with the next step. If it is within a grain, we terminate this reorientation attempt. We do not have to make the next 3 steps. Let's say we have the case as shown here on the right-hand side. We've picked a lattice point that is on a boundary. Let's go to step number 2. Now we select a new orientation, Q nu, which is supposed to be different, of course, from the original orientation, Q mu. To that, we consider only orientations from neighboring lattice points. I suppose it makes sense because, like I said, we want to model grain boundary migration, so the change of orientation from a certain grain to one of the neighboring orientations. So we do not want to have any nucleation events. This new orientation taken from the neighboring grains is assigned on probation. So it means we are not sure yet if this one is the right one. In the third step, we then calculate the energy of both states, the one with the original orientation and the one with the new one that we just assigned on probation. We can use for this the Hamiltonian as it is shown here. Now, the important point is, of course, we can calculate the Hamiltonian for the original state and then for the new state with the changed orientation. But what we need in the following step is going to be the difference in energy. And yes, this is important because think about it like this. In each step, in each reorientation attempt, we change only one orientation of one lattice point. So basically, the vast rest of all our lattice points stays completely untouched. And if we want to calculate the difference in energies, then most of them will not contribute. So the difference in energy can be written in this simplified form, where we consider only the nearest neighbors of our selected lattice points. So what is the outcome? The difference in energy can be either positive or negative, and of course it can be 0. And now in the last step, we select the final orientation Q mu star, which could be either the new one, Q nu, that we assigned on probation, meaning we are keeping the new one, or we are rejecting this new one and we take only the original one that was there already. And we select this new orientation, Q nu with a certain probability. That depends on energy and mobility of the boundaries. You can see an example here in this image. It means if the difference in energy is smaller or at least zero, then we see that with a certain probability, for example, with a high mobility, we see that there is a high probability to accept this new orientation. It basically means that we are reducing the energy of our lattice. And so, yes, we want to do this, so let's do it, and we take the new orientation. However, even if we increase the energy of the system, where delta E is larger than zero, we still may accept it with a lower probability that depends now not only on mobility and energy of the boundaries, but also on the difference in energy. Here we've introduced basically a new parameter, this KBT. KBT, or also often abbreviated as TS, is called a simulation temperature. But it's not a temperature, of course, it's some kind of activation energy. And you can see at the right this image where we see maximum mobility and zero simulation temperature. It basically simplifies our algorithm where we always accept the new orientation if it lowers the energy of the system, and we always reject it if it increases our system's energy. And yes, this is already our complete algorithm. We make these 4 steps for one reorientation attempt, and we do it n times in order to get one simulation time step. So basically, what's the takeaway message? The Monte Carlo POTS model does some kind of energy optimization, or to be more precise, over long time spans, we have an energy minimization. Now, of course, as most models come with some drawbacks, we have some problems also with respect to the Monte Carlo POTS model. And I want to present you 2 and also show you what the solution can be. The first thing is the choice of the lattice. What quite a lot of people do is in 2D, they take a quadratic lattice. Yes, of course, there is also the possibility to select a triangular one. But the quadratic lattice is also something that I personally like very much because it allows you a very easy implementation. You can simply use a bitmap image of your microstructure and simulate on the bitmap, or take a simple matrix. The question is, does this underlying lattice influence the simulation results? And the answer comes from the POTS model itself. The POTS model algorithm simulates curvature-driven kinetics. It means that we have the energy minimized by decreasing the boundary length of each boundary and, of course, then of the total boundary length. But as a result, the driving force of this simulation places the boundaries along the lattice facets. The result can be seen here. You see that the boundaries are very straight, not to say they are more or less linear. And you see that apparently we have very peculiar angles. At each triple junction, at each triple point, we have one angle that is 90 degrees and 2 further angles that are 135 degrees. And this is just wrong, because I've mentioned before that when all our boundaries have the same energies, the angles at such triple junctions should be 120 degrees each. And of course, this is apparently not the case. So where's the solution? The first thing is you should increase the number of neighboring lattice points. In this particular simulation, I have used in 2D on the quadratic lattice only the first nearest neighbors. So left, right, up, and down. In addition, you should use at least the second nearest neighbors also. And you should give them a weight. This actually makes the simulation slightly better. However, there is a second possibility. You should actually introduce the simulation temperature KBT, because KBT activates thermal fluctuations that roughen the grain boundaries. The question is, how do I select it? Because the simulation temperature is not related to any real annealing temperature. And usually quite a number of colleagues find it by trial and error. But at least to me, trial and error is not good enough. You see here an image of a circular grain that is embedded in a larger grain. And I've selected KBT, the simulation temperature, as 0. And you can see that even for a circular grain, some of the boundaries actually align with the underlying lattice, so they take horizontal, vertical, or diagonally shapes. We do not want this. So we increase KBT. And if we do it by trial and error, just pick one, we see that if I just select this one here, apparently my grain boundary becomes extremely rough. And if I go even beyond, I will realize that my grain is just going off. It's no longer a consistent grain. There are bits and pieces of the grain that just go away from the grain, and it's of no use. So I have to go to smaller simulation temperatures. But which one? You can see here that, yes, this one looks good. 0.66 joule looks good, but how do I get something like this? And not by trial and error. To that aim, I have simulated the circular grain embedded into a larger grain multiple times. And I have varied systematically the simulation temperature. What you can see is that apparently the area is a linear function of annealing time, which you should always test if you have implemented your algorithm in U. This is a really good test. The area of any grain that you put into it, embedded in a larger grain, should always be a linear function of time. But you can see here that apparently the slope changes with simulation temperature. The larger the simulation temperature, the smaller the slope. However, we know from theory of von Neumann and Mullins that the area change rate depends on the number of edges, or to be more precise, on the number of triple junctions, where the only two parameters are mobility and energy of the boundaries. And this is really a great opportunity to test our model case. Because if we put a circular grain into it, such a circular grain does not have a triple junction. So n equals 0. Hence, the area change rate should be minus 2 pi multiplied with mobility and energy of the boundaries. For my current test case, I have taken mobility and energy to be equal to the maximum mobility and energy in the simulation. As a result, I can say that m and gamma are equal to 1 without writing any units here right now. So the area change rate of such a grain embedded in a larger matrix grain should be minus 2 pi if it's a circular grain. Now I can plot the slopes that you can see here as a function of the simulation temperature. And the result? Well, we see that apparently the area change rate is indeed a function of the simulation temperature, and only at one point we get that the slope equals to minus 2 pi. And this is precisely my optimal temperature of 0.664. of course, you should be aware that for your personal implementation, you have to do it yourself, because every implementation is slightly different. For example, when we go back to this point where I said, okay, let's select a new orientation and we take only orientations from neighboring lattice points. This can be done in different ways. You could choose any orientation. Then you are going to reject much, much more, and hence your simulation temperature will be different. Or if you select not from all neighboring lattice points, but just from the neighboring grains, the orientations, it's also always slightly different. But the basic way of how to do it is the same. Take a circular grain, put it into a larger matrix grain, do the simulation for different simulation temperatures, and you'll see at some point your area change rate should be -2 pi. What is the outcome if I take a simulation with -2 pi? Well, you can see here that I've done the same not just for a circular grain, but for different grains with different number of edges and triple points. And I've plotted here the area minus the initial area in order to get this nice image where we see how the area then changes with annealing time. It's always a linear function of time. And we can plot the area change rate as the number of edges, and we can see that basically a linear least squares fit is identical to the prediction by von Neumann and Mullins. So we found for this very implementation just the perfect simulation temperature. What is the takeaway message here? Be careful with your parameter selection. Now, to what problems can we apply this? Of course, we can start with the simplest way. Let's simulate normal grain growth, for example, where all boundaries have the same properties. This is a very good test case if you want to compare your simulation with existing analytic theories. But of course, you could also simulate junction-controlled grain growth, as it may appear in nanocrystalline materials. You can simulate texture-controlled grain growth, or abnormal grain growth, where just a few grains increase their size much, much more compared to the surrounding matrix grains. Or you can simulate grain growth in 2 dimensions, as you can find it, for example, in the 2D material graphene. Or simulate grain growth in thin films, where you have a 3D sample, but in addition, surface effects become most important. Now, of course, I cannot show all of it. I just do not have the time right here. So let's just pick one. And I've selected junction-controlled grain growth because it's very fascinating to go to smaller grain sizes. What is known is that in nanocrystalline grain structures, in addition to the grain boundaries, the triple lines and the quadruple points gain importance. And this is simply due to the fact, if you think about it, compared to your microcrystalline sample, a nanocrystalline sample, yes, if it has the same total size, it contains the same volume, of course. But the relative volume of all your atoms that are associated with, say, bulk within grains gets smaller and smaller, whereas the volume percentages of atoms that are associated, for example, with triple lines or even with quadruple points, those percentage increases when you go down in size. Hence, you can see here an example of an experimental measurement where the average grain radius has been plotted as a function of annealing time for nanocrystalline iron. And what you see is that apparently after a very short initial period of time, there is a linear relation between average grain radius and annealing time. And this is quite different compared to microcrystalline grain growth in iron. Because if you go to larger grain sizes, you will realize that your average radius is a square root function of annealing time. So apparently, in the nanocrystalline size regime, there are changes in the grain growth kinetics. Now, there has no universal explanation found for this thermal stability yet. But finite mobilities of triple and quadruple junctions are in the focus. And it has been shown analytically that taking finite mobilities of triple and quadruple junctions into account actually changes what we observe. And yes, it changes the square root law from the microcrystalline coarsening regime actually to a linear regime. The question is this really consistent with the experiments? And do we get more information? Do we need more information out of our experiments to prove our analytic theories? And in order to do this, we want to do some computer simulations. What we know from analytic theory is that grain growth is a dissipative process. We can derive 3 different scaling regimes for grain boundary control, for triple junction control, and for quadruple junction control, depending on which mobility for the 3 different features drives our kinetics most. Now, of course, this looks already different. For the 3 different kinetics, we get 3 different scaling regimes, but maybe it's easier for you to look at average growth laws. And by integration, we get those. As a result, grain growth, controlled by the grain boundaries as we observe it in the microcrystalline size regime, gets an average growth law where the average grain size increases indeed as a square root law of time. For triple junction control, we get this linear growth law that we just saw in the experiment. And for quadruple junction control, we get an exponential increase even. But like I said, do we get the same out of a simulation? And can we go beyond with our information that we may get out of the simulation? To that, we use again our POTS model. Now the problem is the POTS model contains only 2 parameters, the grain boundary energy and the grain boundary mobility. However, I have shown that you can include precisely here the separate mobilities and energies for the different grain features. So it basically means that whenever a lattice point that you pick is on a boundary, yes, it gets the energy and mobility of the boundary. If it is associated with a triple junction, a triple line in 3D, then it gets a separate mobility and energy. And also with the quadruple junctions, it gets its own mobility and energy. So let's take this simulation algorithm and actually apply it. First of all, let's do a simple 2D simulation just for this scheme. We have here on the left-hand side the initial structure, basically just 3 grains. And then we take some pictures out of the quasi-stationary state of coarsening. And what we see is in the first image of the simulation, the second from the left, we have normal grain growth. The mobility of the triple junctions is equal to the mobility of the grain boundaries. And we get our 120 degrees angles that we actually really expected to come out. However, if we then reduce our triple junction mobility, we see that the angles change dramatically. And in the end, for a really low mobility of the triple junctions, we get 2 dihedral angles that have only 100 degrees roughly, and one that has 160 degrees. So apparently there are inherent changes in the junctions. Now, what are the changes with respect to the whole microstructure? And to that, let's go to 3D. Do such a 3D simulation and you can see an image here. But what does the kinetics look like? To that aim, let's plot the average growth law. So let's plot the average grain radius as a function of annealing time. And what we see is the upper curve is again normal grain growth, and then we reduce systematically the triple junction mobility. And you can see that if we reduce the junction mobility, we come to a point where we observe for long annealing times actually a linear relation between average radius and annealing time, just as predicted for triple junction mobility analytically. If we look even more closely, we'll see that after a short initial period of time, for example, curve 3 shows a linear relation indeed between average radius and annealing time. However, after quite some simulation time, the simulated curve deviates clearly from the linear least squares fit. And this was precisely also seen here in the experiment. When we go from smaller to larger grain sizes during annealing, apparently also in the experiment, we saw that there are deviations. And apparently for larger grain sizes, our samples tend to go back to the square root law that we've seen regarding their kinetics. And this is pretty fascinating that we can actually model something similar. So it seems actually as if the annealing temperature that we see in the experiment is somehow coupled to our reduced triple junction mobility. Of course, we will need to do further experiments and simulations with this respect. But of course, right now we do have our simulation data available, and what we can do already is we can go beyond average growth law. So, for example, we can have a look at the size distribution, and it's always nice to analyze the scaled size distribution, where we scale it in such a way that on the horizontal axis we have the scaled grain size, which is grain radius divided by average grain radius. So we can actually compare different samples of different sizes, and the integral under our curve is equal to 1. Then we can really compare different samples. What we see here is, by the crosses, our initial grain size distribution, and we see the self-similar state for normal grain growth, for the case where all our triple and quadruple junctions have the same mobility as the grain boundaries. And we see it's quite a nice distribution, a unimodel distribution, somewhere between 0 and say 2.1, 2.2, which means that the largest grains that we observe are 2.2 times the average grain size. And our distribution has a maximum roughly around x equal to 1. Now, what happens if I reduce the triple junction mobility? If I do this, you can see the result here. I have reduced it to 1/8 and 1/16. And you can see that for such low mobilities, we actually still observe self-similarity. So we do have this linear growth kinetics. And in addition, we see that also the size distributions show self-similarities, meaning this scaled size distribution does not depend on the annealing time. But its shape is completely different compared to the one that we see here on the left. Apparently, it's shifted to smaller relative grain sizes, meaning we have more grains with relatively small size. And in addition, it also has a slight tail. So basically, we do have grains that are 2.5, 2.6 times the average size. So the distribution becomes broader and slightly skewed. Now, of course, we could also analyze topology, morphology of individual grains, and so on. But due to the lack of time, let me just point out one more thing. Of course, in addition to the triple junctions controlling the kinetic, we could technically also have the quadruple junctions controlling the kinetics. And the result you can see here. We have again a short initial period of time, and then we observe an exponential increase of the average radius with a function of time. After a couple of hundreds of Monte Carlo time steps, we see that the curve changes, however. This exponential regime is marked by number 2, and then we go over more into 3, which is a linear regime. And finally, it tends to go back to the square root. So this is actually quite nicely in agreement with what we just saw. We saw previously this change from linear back to square root for triple junction control, and here for quadruple junction control, it goes just one step further. The question is, we just saw that the scaled grain size distribution changes not that much, but we see a more skewed behavior, a broader distribution when we go from grain boundary control to triple junction control. Now the question is, what happens for quadruple junction control? And the answer is this. We see, again, self-similarity, but the distribution now shows a huge amount of relative small grains. And the distribution becomes much broader again. So now we have grains that are more than 3 times the average size. And like I said, we have this very particular behavior with this peak at very small grain sizes. Of course, these distributions that we have just seen can actually be modeled analytically. With the help of the computer simulation that we just saw, we were able to derive an analytic theory that is in brilliant agreement with our simulation data. The step that is still missing now is a comparison with experimental measurements. To summarize, computer simulations may close the gap between experimental measurements and analytic theories. However, they may in particular go beyond what we see in experiments or are able to derive analytically. One possible method is the Monte Carlo POTS model. It is simple in its basics. For example, it takes only 2 materials parameters into account. Of course, you have to be careful with the specifics, for example, regarding the parameter selection, but then it is very complex in its possible applications. So it has a broad variety of uses, from normal grain growth to triple junction controlled abnormal or even thin film grain growth. And if you want to read more, just make a screenshot or pause the video to get some more information on what I have done previously. And if you want to ask me something, anything POTS model related, just let me know, contact me. And with this, I would like to thank you for your kind attention. I hope this overview helps you understand the needs for modeling, in particular grain growth, a bit better. And if you still have questions, do not hesitate to contact me. So thanks again for your kind attention.
Chegamos ao final, então, da segunda palestra dessa manhã. Agradeço a presença de todos. A professora Dana não participará de discussões online neste momento. Perguntas poderão ser enviadas a ela através de e-mail que ela deixou no contato no final de sua palestra. Bom, eu também gostaria de enfatizar o agradecimento à professora Dana pela brilhante apresentação, que a professora receba nossos cumprimentos de forma remota pela excelente palestra. Adicionalmente, eu gostaria de agradecer ao professor Paulo Rangel pela introdução da professora Dana, que ele fez no início da palestra. Bom, agora a gente vai seguir para a palestra do professor Leonardo Godilho. Então, nos vemos daqui a 5 minutos para outra apresentação. Até mais. Olá.
¿Cómo estás, Leticia? ¿Cómo va ese día?
Estou bem. E você?
Bien, también, todo bien.